Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure to introduce Michael Levesky from Stanford University in the Graduate School of, it's the Business School at Stanford. He's going to be presenting a talk today on generalized second price auctions that I think is of a lot of interest to all of us who are thinking about search auctions. Please welcome Michael.
Thank you, and thanks for inviting me. As Chris said, the title of the presentation is Internet Advertising and the Generalized Second Price Auction. And this is joint work with Ben Edelman, who is at Harvard, and Michael Schwartz, who is at UC Berkeley. So I'm sure most of you know what those search ads are, and you've seen them, but just to make sure that we're all on the same page, let me give a very brief introduction. So if you go on any search engine, so here I went to MSN and type in some search terms such as car insurance, you get real results, which are in the lower left corner, which are the results that are returned by the search engine. And then you also get advertisements, which are up there on top, in the red rectangle, and also to the right. So all of those things are sponsored search ads. They're advertisements from various websites. And the way you get your ad into one of those places is through an auction. So this is, in that particular case, those results are powered by Overture. The ads came from Overture. And you can go and see through Overture bid tool, you can see what the bids for those keywords are. In this case, this is for car insurance. The top one was from Progressive, which was $13.58 per click. Then the next one was $11 per click, and so on. So before I go into the details about the auction that is used to allocate those advertisements, let me give you a few facts about the environment. So first of all, the auction is very much specific to the environment of online advertising. This auction would not be applicable to pretty much anything else. There is no other setting where this particular mechanism would make sense. So it's very specific. On the other hand, this environment is very important. So Google's revenue in 2004 was $3.2 billion, and over 98% of those revenues came from the generalized second price auction, from this mechanism. Yahoo's revenue in 2004 was $3.6 billion, and more than 50% of the revenues came from this mechanism. So just to give you a sense of magnitude, if you add up those revenue numbers, divide them by the US population, that's about $20 per person in the US. So those are very large numbers. And there are several other companies that use this generalized second price auction. I don't know what you guys are going to use when you launch your own search ad, the engine for selling the ads, but other companies are also using this. And just to give you another sense of magnitude, so the market cap comparison of Yahoo and Google, which are based entirely on this thing, is about $125 billion, whereas if you take all the US airlines combined, their market cap is about $20 billion. And I guess now it's even lower now that two of them went bankrupt a couple of days ago.
Yeah, but
so,
they have negative earnings, right? Or negative.
Well, not all of them. Some you have JetBlue, have Southwest, and they have.
No, JetBlue's negative.
Okay, Southwest. So market cap of Southwest is about $10 billion, and that's a very successful airline. So just it's a very even though this mechanism is applicable to only one setting, this setting is very important. So how exactly does this work? And again, I'm sure most of you know this, but just to make sure that we're all on the same page. So the bids are per click. So those numbers that you saw there, the $13, the $11, that was how much Progressive was willing to pay to the search engine if someone clicked on its ad per click. You submit just one number, which is your willingness to pay per click. And the higher the number, the higher your ad goes on the screen. Now, that's assuming that the click-through rates are the same for everyone, and I'll get to that in the next slide. But roughly, you should think of that. The higher your bid, the higher on the screen you go. Now, the key twist of this mechanism is that you do not pay your own bid. You pay the bid of the next highest bidder. So if you go in position 5, every time someone clicks on you, you pay the amount of money that that bidder 6 bid on this particular keyword. And that's why we call this auction generalized second price. Because with only one object, if you only had one slot on the screen, then this would be exactly identical to the standard second price auction. You get the object, you pay the second highest bidder's bid. But here you have multiple slots, so it's a generalized second price auction. And another neat feature of these auctions is that bids can be changed at any time. You can, if you're unhappy with the current bids, you want to be higher or lower, you can go change your bid, and then next time someone enters the search term, your ad will be displayed in accordance with your new bid.
It's only half true. I mean, on Google it takes something like 24 hours or so before the new one takes effect. So, which means millions of searches later.
Okay, so I guess what I have on the screen is 100% true, but what I didn't say there is that you can change the bid at any time, but it won't take effect for a while. Right. So, and actually, I do not know whether that's for some substantive reason or some technical limitations. I just do not know. And it's something to think about how often you should let people change their bid and what the delay should be.
Are you considering click-through rates in this mechanism?
Sorry?
Are you considering click-through rates in this mechanism or not?
So that was the next slide, and thanks for asking the question. So the click-through rate is the probability that a particular ad will be clicked. And of course, if you're in different positions, if you're on the top of the screen, then you have a much higher probability of being clicked than if you're at the bottom. So in this paper, we assume that all ads have the same click-through rate if they're placed in the same position. So if my ad is in position 3 and your ad is in position 3 for a particular keyword, they will get the same click-through rates. And so for that reason, we can just ignore all of the issues that arise when click-through rates are different. So in a sense, Yahoo makes the same assumption, quote unquote, because what they do is they just rank the ads by the bids, as I described. Now, Google makes a slightly different assumption. What they do is they multiply the bids by the estimated slot 1 CTR. So what they do is they said, if you put this ad in the first position, what would be the click-through rate there? And they take this number, they try to estimate it statistically, and then once they get the number, they say, okay, they multiply that by the bid, and that's how they rank. That's how they rank advertisements. And sort of the economic assumption that this procedure implicitly makes is that if my ad is twice as likely to be clicked as yours in position 1, it will also be twice as likely to be clicked in position 3. So this sort of the ratio of our click-through rates will be constant for all the positions. And in fact, our analysis can be readily extended to that case. So that's not going to be much more complicated. What we cannot handle using our techniques is the situation where my ad has a particularly high probability of being clicked in position 3, and your ad has a particularly high probability of being clicked in position 5. So when we have those very specific advertiser position effects, and we cannot handle that, and both of those search engines ignore this possibility, so we do not know how important this is empirically. My suspicion is that it's not particularly important, but who knows? So let me give you some history, some background on how this thing happened. There were recent auctions that were designed by economists essentially from scratch. The spectrum auctions, the electricity auctions, there was nothing there, and then someone came in and basically designed an auction to allocate the goods. Now, in contrast, sponsored search auctions evolved over time. It wasn't just someone just came in and introduced this mechanism. Sort of there was a process of evolution. It started in 1994, where you had banner ads. I'm sure you all remember and love banner ads. And it was per impression pricing, based on largely on person-to-person negotiations, where and how you put those ads, and there was no keyword targeting. It would basically just bombard everyone with those banner ads, and that was essentially it. It was just sort of like TV advertising. Then in 1997, Overture, which was then called GoTo, came up with a brilliant idea. They introduced what we call generalized first price auctions. So they introduced the idea of the pay-per-click pricing. They also introduced the idea of keyword targeting. So advertisers could go and bid on keywords. It was all completely automated, and bids could be changed at any time. Again, I don't know what the delay was, how fast those bids would be taken into account, but I think it was pretty fast. The links were arranged in the descending order of the bids. So far, this is exactly the same as the generalized second price auction. And the difference was that you pay your own bid. So that's sort of, that as a first approximation, it makes sense. You ask people how much they're willing to pay. You rank them in the order of their bids, and then you charge them whatever they said they were willing to pay. So it seems to make sense, except that there is a problem. And the problem is that the generalized first price auction is unstable. It's unstable in the sense that it does not have a pure strategy equilibrium, and bids can be adjusted dynamically. So here's a very simple example. There are 2 slots and 3 bidders. The top slot gets 200 clicks per hour. The second slot gets 100 clicks per hour. And the bidders 1, 2, and 3 have values per click of $10, $4, and $2, respectively. So suppose bidder 3 bids $2 and just goes home. He doesn't change his bid. He just bids $2. Then bidder 2 comes in. He sees that bid. He wants to overbid that third bidder slightly, so he bids 2.01. Because he doesn't want to bid anything higher, because then he will be paying the extra money without any change in his position. There is no reason for him to bid anything higher. Then bidder 1 comes in, and he bids 2.02. Because again, he can get the top position for that amount, and he doesn't want to bid anything higher, because he pays his own bid. Then bidder 2 sees that, and he now wants to outbid bidder 1 by bidding 2.03. Then bidder 1 comes in and bids 2.04, and they keep increasing the bids by a penny until they hit, let's say, $4, at which point bidder 2 says, well, I no longer want to compete for the first spot. This is my limit. So he drops back to $2, at which point bidder 1 comes in and jumps it at 2.01, and the whole process restarts. Right? So it sounds like it's a hypothetically interesting possibility. Turns out that that's exactly what happens in real data. So this is data that we have from Overture for a particular keyword. I think it was June 2002. I don't remember the exact date. It's in the paper. And that's exactly what you see. So there are 2 bidders. They start at point A. They start outbidding each other. They reach some level. Here it's $10 to point B, at which point one of them drops to $6, and the whole process restarts. And of course, it's not like there are 2 people sitting there changing their bids. They have their automated agents, but that's the way those agents were programmed. And it made sense to program them in this way because there is no pure strategy equilibrium. So you get this instability. And in fact, you have the same thing for most keywords, for most time periods. So you have the same thing over a week. Yes?
It's true that it's not stable, but you're still getting more revenue than you would with a second price auction there. Because the second price auction would say you pay $6 if you had your 10 and your 6. And here you're getting at least $6, sometimes more.
That's actually, so we have a separate paper with Ben. It's a short note where what we did using this data, we said, let's compute their revenues, and let's compute the counterfactual revenues if they were using the second price auction and everyone was bidding truthfully.
Right.
And in fact, revenues are higher under the second price auction. And the reason for that is...
Oh, but that's if they were bidding truthfully.
If they were bidding truthfully.
But second price
these are not bidding truthfully.
These are not bidding truthfully either.
So
And second price is not a truthful auction.
Okay, so we also...
So those assumptions don't make any sense.
So we also did a thought experiment of comparing those revenues with VCG revenues.
Right,
Which,
that's truthful.
There the results are less clear cut, but the results are if you have few bidders for a keyword, if you have 1 or 2 or 3 bidders, then it's better to use this cycle, the first price mechanism with cycling. But for active keywords, which we think generate most revenues, it is better to use VCG. You get higher revenues under VCG than you do in this cycling mechanism.
I see what you're saying. My only point is that somehow the second price doesn't have the advantage of the VCG in being truthful.
That's basically.
But it also doesn't have the advantage of the first price, which earns more revenue. So it's kind of interesting.
So I mean, your first point is going to be half of our paper. Like basically, our paper is about comparing the GSP with VCG. Your first point about comparing second price with the first price. I mean, the problem with the first price auction is that it gives you just such strong incentives to constantly sit there and monitor your bids. Basically, the whole game becomes not about figuring out good keywords, not figuring out good advertisements. It becomes about, writing an agent that can respond to others as fast as possible. And that's just totally inefficient investment. It puts huge pressure on Yahoo servers, for example. Just you get tons of bids all the time. They want to change their bids all the time. And you also get lower revenues, although we can talk about that.
Okay,
we can talk about this later.
Randomized equilibrium here, if they are not, for this example.
Sorry?
For this example, what is the randomized equilibrium when they are tossing coins and randomly deciding their bids?
Oh, you mean
mixed
strategy equilibrium?
Yes.
There is some mixed strategy equilibrium, but you wouldn't use it here, right? Because it's a dynamic auction, so there is no, you would only use a mixed strategy equilibrium if you have just one-shot simultaneous move game. But here, there is no reason to randomize because you see what everyone else did. So in the next 5 seconds, you just go and bid your optimal bid against
it. Everybody just tossing coins, and then nobody tells me what they are before the auction.
No, but the auction happens continuously. So in a sense,
I just give my coins to Yahoo, and Yahoo just keeps tossing coins.
Oh, you could do that.
Then what is the equilibrium in that case?
The answer is I do not know. You can probably figure it out. I mean, they could have done it this way, absolutely. But I don't know what the equilibrium would be. So this was the problem. You have all this cycling, you have all this investment in inefficient technology, and when Google introduced their mechanism, they basically fixed that problem, at least partly, by saying that instead of paying your own bid, you pay the bid of the next highest bidder. Right? That was essentially the change that they made. They also made this multiplication by click-through rates, which we ignore in this paper. And this design was later adopted by Yahoo and Overture. They basically pretty quickly realized that it's a better way of doing things, so they switched to this generalized second price auction as well. And right now, this is the state of the art. This is what all of them are using. And again, I don't know what you guys are going to use when you implement this stuff. And it looks like Google, when they were introducing this thing, it looks like they thought they were introducing the Vickrey auction. So here's a quote from their marketing materials, which I'm sure they won't be there in a few weeks once they get this paper. But fortunately, I saved this PDF file on my hard drive, so I have it. And the quote says that Google's unique auction model uses Nobel Prize-winning economic theory to eliminate that feeling that you've paid too much. And then they mention Vickrey. Right? So it looks like they thought they were using the Vickrey auction, and it's clear why they thought that, because if you only had one slot, then GSP is identical to the standard second price auction, which is also known as Vickrey or VCG. Now the problem is that with multiple slots, the mechanisms are different. So GSP charges bidder I the bid of bidder I plus 1, whereas VCG charges bidder I for the externality he imposes on everyone else. So let me clarify the difference. So let's go back to the original example. Same setting. There are 2 slots, 3 bidders. First slot gets 200 clicks per hour. Second slot gets 100 clicks per hour. Bidders have values 10, 4, and 2. And suppose for a second that they bid truthfully. They bid 10, 4, and 2. So under the generalized second price auction, the payments are straightforward. So the guy who gets slot 1 pays $4 per click, and then the next guy pays $2 per click, and the total payments are $800 and $200 respectively. Now under VCG, the amount that the second guy pays is the same as under the generalized second price auction, because we assume there are only 2 slots. So the externality that this guy imposes is basically he kicks out the third guy out of position 2, so he pays the value of the third guy, which is 200. Now the payment of the first advertiser is different under VCG. What the first advertiser pays is the externality he imposes on the remaining 2 guys. What is that externality? So he imposes the externality of pushing the third guy out, right? So that's 200. And then he also imposes the externality on the second highest bidder by shifting that bidder from position 1 to position 2. Right? So he basically just stole 100 clicks from that guy, and that guy values those clicks at $4 per click. So the externality he imposed on the second guy is 400. The externality he imposed on The third guy is $200. So the total externality, the total payment of the first bidder under VCG is $600. And of course, if you had more slots, then under VCG, the externality that a guy in position I imposes is the externality he imposes on the guy in position I plus 1 by shifting him by 1 position down. Then he also shifts the next guy by 1 position down, and so on. So his total VCG payment is the sum of those numbers. Okay, and that's a different payment scheme from the GSP auction. That's why they're different. So any questions so far? Because now I will jump into the notation and the theorems. Once we have notation, we can prove theorems. Okay.
Well, I have
Yeah.
a question. Is it possible to come up with an example where second price cycles, when generalized second price
Where it,
cycles like you did in the first price?
I'll give you an example in 2 slides where there is no pure strategy equilibrium. And then, whether it will cycle or not, I don't know, because we don't have the data. We would love to get the same data for GSP and show that one also cycles. I mean, the thing with
But
cycling.
in theory, can you find a theoretical example where it would cycle?
I mean, the thing about theory is that, in theory, you can come up with anything, right? I'm serious. In repeated games, you can come up with pretty much anything. If it's not incentive compatible, if there is no pure strategy equilibrium,
No, it could be, for example, that instead of cycling, it drives the revenue to 0. That would be another possibility, right? So.
Yeah. I guess the reason why we like cycling so much.
It would be interesting for me because I might prefer cycling to having revenue 0.
Sure. Right. No, I understand.
Details.
No, I understand. I mean, the reason why we took the cycling example, the intuition is very natural, and we looked at the data, and it's just there. So, I do not know. I don't have the data. I don't know what happens in the data for the second price auctions.
So I've done simulations, and I haven't seen cycles
You haven't seen cycles in
my simulations.
second price auction.
Yeah.
So what did you see?
I saw converging to different equilibria depending on what I picked as the bidder strategy. And it turned out to matter. I didn't try that much, but when I tried one strategy where you bid 1 penny more, one penny, you bid the minimum you had to, and I did another one where you bid the maximum you had to. The maximum you could, because there's a big range that will get you identical results. And depending on whether you bid at the bottom or at the top, the auctioneer got either a lot less or a lot more revenue. But I didn't see cycling.
Okay.
I think that
Did you see cycling with first price?
I didn't simulate first price, but I'm aware of these examples, and it seems like predictable behavior.
And all your bidders have the same strategy?
Yeah. I don't mean to interrupt your talk. I'm happy to go offline with anyone.
No, and that's that. Well, we'll talk about that. That sounds very interesting. So let's get back to theory. So let's say there are n objects and k bidders or advertisers. Let's say that alpha I is the expected number of clicks in position I, and sk is the value per click to bidder k. So the total utility of a bidder is alpha I sk minus the payments to the search engine. We assume that those positions, the higher you are, the higher your click-through rate. So alpha I is greater than alpha 2, greater than alpha 3, and so on. Now let's say that B sub j is the bid of the jth highest bidder at a given time. So they all submitted their bids. So that's the jth highest bidder, and g of j is the identity of this guy. And then according to this mechanism, g of 1 gets the top spot, g of 2 gets the second spot, and so on. The payments are the payment of the guy who is in position I, P sub I, is equal to alpha I times B sub I plus 1. So it's just formalizing the fact that you pay the next highest bidder's bid. And then his payoff is equal to alpha I times SI minus B I plus 1. Right? Very straightforward. We just wrote down what I explained earlier. Let's also do the same thing for VCG. So the notation remains unchanged. And the allocation rule is also the same. The higher you bid, the higher you are on the screen. The payments are different. So the last bidder who gets an object gets the same payoff in both mechanisms, right? So for him, the payments are the same. Now, for all the other ones, for all the guys higher than him, those payments are defined recursively. So the payment of the guy in position in position I, P sub VI, that's the payment under VCG of the guy who gets object number I, is equal to alpha I minus alpha I plus 1 times B sub I plus 1, which is the externality that he imposes on the next guy, plus P V sub I plus 1, which is the externality that that next guy imposes on everyone else. So any questions about this formula? Because that's basically how VCG works, and that's important to understand where it comes from. Right, so once again, in this formula, there are two terms. So the first term is the externality that player I imposes on player I plus 1. And the second term is the externality that he imposes on everyone else, which is the same as the externality that player I plus 1 imposes on everyone else. So if you expand this, you will just get a series, which is exactly what I said. It's the sum of those externalities of shifting everyone by one place down.
Or you can just throw out the one person and recalculate, and you get the same answer.
Yeah, you'll get the same answer.
Right.
Right, exactly. That's
the easiest way to think about it, I think, even though I'm not sure. Well, whatever.
Yeah. But then that's the formula.
Yeah.
Now, two remarks. First remark, that under VCG, at least when there are no budget constraints, we know that it is a dominant strategy for all bidders to bid their true values. Right? That's a standard result. That's why Vickrey got the Nobel Prize. The second remark is that if all advertisers were to bid the same amounts under the two mechanisms, then each advertiser's payment would be at least as large under GSP as under VCG. So again, you take the same bids. If you assume that they bid the same, the revenues would be higher under GSP than under VCG.
If under GSP, but that's assuming that it's...
That's exactly right, which is why it's just a remark. Okay. It's just a remark about mathematical inequalities, right? Now here is the problem. Here is basically the starting point of our analysis. Here is why we wrote this paper. The problem is that truth-telling is not a dominant strategy under GSP, and there is no equilibrium in with truth-telling under GSP. It's not optimal. You would not necessarily want to do it. Here's a very straightforward example. Suppose, again, there are 3 bidders, 2 slots. Values are as before, 10, 4, and 2. And click-through rates are 200 and 199 clicks per hour. So they're almost the same. Now, if all bidders bid truthfully, then let's compute the payoff of bidder 1. So he pays $4 per click. He gets $10 per click. So his net payoff is $6 per click. He gets 200 clicks. So his payoff is $1,200. Now suppose that instead of bidding truthfully, he undercuts bidder 2 and bids only $3. So now he gets position 2 instead of position 1. So he gets only 199 clicks per hour, but he only pays $2 for this position. So his net payoff is 8 times 199, which is almost $1,600, which is more than he would get if he bid truthfully. So this is basically the starting point of our analysis, because that's why this whole problem is interesting. So any questions about the example, about why? Yes?
Your example has a second line almost as valuable as the first line. Now, the people who are actually selling ads say that basically all the money is in the first line and the rest is petty cash. And how does that affect at least the numerical size of your counterexample?
So you're right that it's an empirical question. It's clearly not true that all values in the first slot, because if you go there are 10 people, and the remaining 9 people compete for the remaining 9 slots. So apparently there is some money in those 9 slots as well. So even if for the top slot you want to bid your true value, well, the remaining guys may want to do something.
Especially when you bid per click, it doesn't cost you much to be pushed to the second slot and make a little bit of petty cash and pay a little bit of petty cash back. But in terms of the way people set their budget, do they care?
The answer is I do not know. And then the problem is we're theorists, we don't have data. We would love to get data.
I'm sorry?
We would love to get data and be able to answer your questions. If you have data, please send it to us, and we'll answer your question.
So you would say that in designing an auction, you would actually want to consider what the effective number of clicks per position would be and try to design the layout in such a way that it would cause those click rates?
it's not just the effective number of clicks, but there are data which indicates that your sales per click are much higher from position 1 than from position 2, and much higher from position 2 than from position 3.
Right,
and clearly this is, so your conversion rate is different.
So we ignore this effect. And I actually don't, I mean, that was not my impression. So from asking those people, they tend to think that if anything, it's best to be, for conversion rate, it's best to be in position 4 or position 5.
Right.
And in position 1. Sorry?
There are data which sort of contradicts it.
Maybe also other data.
Yeah, there is. I can send you the paper which it was by Atlas one point which they did this analysis, and sort of just talking to the bidders, they seem to think, some of them seem to think that it makes no difference where you are for conversion rate, and those tend to be sort of the ones who are more clueless, and sort of the more intelligent ones know that there is a difference, and they usually say, it's a few percent more in position 4 and 5. So, but I don't know. It may also be true that for different markets the effect is different. For some keywords, yes.
But I think that the point here was just that even from a theoretical point of view, if you assume that most of the clicks are coming from the first slot, if you look at asymptotically that case, you'll find that this difference will tend to 0 as the value of the
just
first
scale the value of the person who's winning in the the score in 2. You can scale them to be very different, and then you're still going to get a strategy for the high bidder.
Yeah. Anyway, but let me move on.
One other thing that wouldn't be truth-telling in a GSP would be the cycling of, in the case of the 10, $4, and $2 bids, the $4, the second advertiser whose value is $4, has value in saying that he actually has more value than he does to charge more money to the first advertiser.
I'll get to that. I'll definitely get to that. So, so that was basically the starting point of our analysis. Was say, the truth-telling is not necessarily an equilibrium of GSP. So, what are the equilibria of this generalized second price auction? This important mechanism. And one problem that we immediately ran into is that it's a dynamic game. It's an infinitely repeated game, and from folk theorems we know that the set of equilibria in infinitely repeated games is huge. Basically, pretty much anything can happen. So we took 2 different approaches to analyzing this problem. And the first approach was just said, suppose for a second that bids stabilize. Suppose we observe some market and they play around for a while, and then bids stabilize at some values. What can those values be? So where can the system converge? And the way we model this, we say, okay, so this is going to be a one-shot static game, sort of like a second price sealed bid auction. And what are the restrictions on behavior of those agents in this game? So the first restriction is natural. All bidders have to play static best response to everyone else. Because if that's not true, then you will have an incentive to change your bid, so it can't be that you're stable. Now, the second restriction is intended to kill the following example. Suppose you have a single object auction, just a second price sealed bid. My value is 1, your value is 2. I bid $1 million, you bid 0. That's an equilibrium, because I cannot change my bid and get more, and you cannot change your bid to get more. But that's kind of a weird equilibrium. We don't believe that this could happen in reality. And the reason why we don't think it can happen is because if you see that, you see that I pay $1 million, you will increase your bid. You will increase your bid to $2, and now suddenly I will change. I will drop out. I will no longer bid $1 million because it will be painful for me to do that because my true value is just $1. Right? But that's a dynamic argument. That's a restriction that the dynamic structure imposes on the game. And in the multi-object setting, we formalize it as saying that the equilibrium has to be locally envy-free, which says that no bidder wants to swap positions and payments with a bidder right above him. Right? So in the example that I gave you, you sort of didn't get an object, but you could force me to drop, to go away by increasing your bid. Here it's the same thing. Suppose I'm in position I, and I want to displace the guy 1 position above me. What I can start doing is I can start increasing my bid. Right? And no one notices that. It has no effect on the payoffs of other guys, except for the guy right above me. Right? So he suffers. What's the worst thing that he can do? he can undercut me just by just 1 penny. Right? That's the worst thing he can do to punish me. So what happens if he does that? It's exactly what I just described. We swap places. Right? I got his position, and I got it at the price that's roughly equal to my bid. It's like 1 cent, difference of 1 cent. We can ignore that. Right? So the assumption is that those situations do not happen, because otherwise you would want to push him out. So those are the 2 assumptions. Yep.
Well, first of all, for the first assumption, you're assuming that strategies that they play are static, but also are you assuming that the off-equilibrium strategies are also static?
We're just assuming a static game. We're just looking at the one-shot game. We're ignoring the dynamic structure. We're just assuming a one-shot game.
Right, but your justification word was that you're looking at the repeated game and you're looking at the convergence. But
yes.
It's true that at the conversion, at the point that they were converging, they might be playing a static
right.
strategy.
Right.
But the reason that they're converging there might be because their off-equilibrium strategies are not static.
I understand. Yes, that's exactly. And that's the problem. If we look at the entire set of dynamic strategies, it's a non-starter, and it's a non-starter because the set is just so huge. And another reason why we don't want to look at those really complicated strategies is we actually looked at the bidding software that those guys use, and the bidding software wouldn't let you do those complicated strategies. So, for example, this bidding software doesn't let you condition your actions on the actions of your particular opponent. Right? So if I cannot say that if this particular person changed his bid, retaliate, and if that the other person does it, do not retaliate. So those strategies are not.
From a theoretical point of view, this is a single-shot game.
This is definitely. This is a single-shot game with commonly known values. It's very simple. The most basic setting.
And for the second property, you're assuming that if 2 people swap their position, then both of them will be unhappy?
No, just one. It's not about swapping. It's just if I'm in position I do not want to swap positions with the guy 1 position above me. That's the only assumption. I do not want to push him out. The other way follows from restriction 1, because if he wants to swap positions with me, he can just underbid me by 1 penny. So he can do it. So it turns out that, so we'll look at these equilibria. It turns out the set of these equilibria maps very nicely to a matching problem. And it's a matching problem with payments. It's a framework of Chaplin-Schubeck 1972. So let's think of positions as being independent, as being independent agents. And let's think about the advertisers who wants to get allocated to those positions. So the value of advertiser position pair, IK, is alpha k SI. That's the value that this pair generates. PIK is the payment of advertiser I to position K. And the advertiser's payoff is alpha k SI minus PIK. Right? So it's an assignment problem with wages. And it sort of looks kind of similar to the original problem of the auction. And it turns out that there is a very neat mathematical correspondence. The first result is that the outcome of any locally envy-free equilibrium of GSP is a stable assignment. And the intuition for that is that if I do not want to swap with the player 1 position above me, if I do not want to steal his position, and he does not want to steal the position of the player 1 position above him, then you can write those 2 inequalities, and they imply that I do not want to steal the position of the guy 2 positions above me. It's very natural. The second lemma says that if the number of bidders is greater than the number of available positions, then the other way also goes through. Any stable assignment is an outcome of a locally envy-free equilibrium of GSP. So what this says is that if you want to characterize the set of those equilibria, you just need to figure out the set of stable assignments. And there are a bunch of algorithms for finding those sets of stable assignments with wages. So it's very neat. Here's another result, which is quite interesting. We have this set of stable assignments. And it's a fact that sets of stable assignments have extreme points. Right? There is a point that's preferred by all advertisers and least preferred by the search engines, and the other way around. So here is one of those points. Turns out that the following strategy profile is very special. Let's say that everyone bids in such a way that the payments of people above them coincide with VCG payments. So more formally, the bid of bidder I is equal to PVI minus 1 over alpha I minus 1, where PVI minus 1 is the VCG payment of the player in position I minus 1. And then the first bidder just bids his true value. Right? So by construction, in this strategy profile, the payments will coincide with VCG payments. Now, it turns out that this is a very special strategy profile. So first of all, it is a locally envy-free equilibrium of GSP. And in this equilibrium, payments coincide with VCG payments. And in any other locally envy-free equilibrium, the payments of bidders and the revenue of the seller are at least as high as in this special profile B star. So in this way of formalizing the game, it turns out that in any stable equilibrium, in any locally envy-free equilibrium, revenues under GSP will be at least as high as under VCG. And the intuition, as I won't go through it, is basically that under this strategy profile, each player is indifferent between his own position and being one position above at his current bid. And that basically gives you both the VCG and local envy freeness. So that was the first way of formalizing this game. But then it was, in some sense, sort of too artificial because we assumed that everyone knew everyone else's values. And it's just a static game. So the question is, how do they converge? We just assume that they converge to this equilibrium. How can they converge? How do they converge? And here it turns out that there is a very natural, very simple way of converging to an equilibrium. And just think about it as everyone comes in and starts at 0. They start bidding 0. And then they keep increasing their bids as long as it is profitable for them to do so. A very, very natural set of strategies. And it turns out that this gives you unique predictions. We model this as a clock auction. So, with the one object English auction, you have a clock. And basically, the last person standing gets the object at the price where the next person where the second to last person dropped out. Now here, the setup is exactly the same. There is a clock showing the current price, and this price continuously increases over time. A bidder can drop out at any time, and his bid is the price at which he dropped out. Then the allocation is very natural. The later you are to drop out, the higher the position you get. The last person to drop out gets the top position. The next to last person to drop out gets the next position, and so on. And the payments are computed according to GSP rules. You pay the amount that the person who dropped out before you, where he dropped out, that's the amount you pay. Now, bidders' values are private information and drawn randomly from commonly known distributions. So this is an incomplete information environment. I know my value, but I do not know the values of other guys. I only know the distributions from which those values came from, and we only assume that those distributions are non-degenerate. There are positive sort of probabilities everywhere, and there are no point masses, that sort of thing. And we also assume, for simplicity, that there are at least 2 slots, and k is equal to n plus 1, so there is one more advertiser than positions. So that makes life a little bit simpler. Now, a strategy is just the price at which you drop out as a function of a bunch of things. So the strategy is P sub I of K, H, and Si, where I is the index of the player, basically player I. Si is the value per click of this bidder. Pi is the price at which he drops out. K is the number of bidders remaining, right? Because if there are 2 bidders remaining and 5 bidders remaining, he will want to drop out at different prices because his values for those positions are different. And H is the history of prices at which bidders K, K minus 1, etc. through K plus 1 have dropped out. If this bidder drops out right now, and let's say there are K players remaining, he will pay BK plus 1, which is the price at which player K plus 1 dropped out. Okay, so this is the setup. Those are the strategy of the agents.
So you have to some extent, again, single shot, right? Because if I repeat it, I can see, last time the guy, I dropped out at this point, but after me, somebody dropped out. He dropped out at this point, so maybe next time I should.
We'll get to that. It turns out that that's not true, in the sense that the outcome will be such that you will not want to change your bid, even after you see. But let me get to the next slide. So here is the next slide. And here is the main result of the paper. And the main result of this paper says that this generalized English auction has a unique perfect Bayesian equilibrium. This unique perfect Bayesian subject to a technical restriction. This unique perfect Bayesian equilibrium is such that each advertiser drops out at the following price level: P, I, K, H, K, H, S, I is equal to Si minus alpha K over alpha K minus 1, Si minus Bk plus 1. And this formula came from the following inequality. Everyone drops out at the price level where he is indifferent between getting position K plus 1 at the bid Bk plus 1 and getting one position above at that price. So at the price where he becomes indifferent between the two, he should drop out. And it turns out that in this equilibrium, each advertiser's resulting position and payoff are the same as in the dominant strategy equilibrium of VCG. So again, we get this sort of profile B star. We get again to the same point. And answering your question, this equilibrium was exposed. The strategy of each bidder is a best response to other bidders' strategies, regardless of their realized values. So it's a very remarkable property. It says that, first of all, you will not want to change your bid once you see everyone else's bids. And second, you do not care about those distributions of types. The equilibrium does not depend on beliefs. It does not depend on the distributions as long as they're non-degenerate. The only thing it depends on are the realized values. And that's actually quite rare. So let me very briefly go through the intuition of the proof. The intuition is actually very straightforward. Suppose there are K players remaining, and there is some price level at which I'm indifferent between getting position K at the current going price and position K minus 1 at that price, at the price on the clock. Then it is a dominant strategy for me to drop out before that. I do not want to drop out before that because at those prices I strictly prefer to be higher. So I will wait at least until that level. Now suppose for some set of types it is optimal to wait longer. Not drop out where they're indifferent, but wait longer and hope that maybe several other people will drop out. Now it turns out that for those, take the set of types, take the lowest type from this set, and it's more technical because it's continuous, so you can't just take the lowest type. So there are lots of technicalities, but roughly take the lowest type who waits longer than optimal, who waits longer than this borderline price level, and suppose the price reached this borderline level. Now this guy knows that he's the lowest type remaining. He knows that everyone else has a higher type than he does. He also knows that none of them will drop out too early. They will only drop out at prices where they are indifferent between getting a higher position and the current position. But he has a lower type than all of those remaining guys. So if they are indifferent, then he would strictly prefer to get a worse position at a cheaper price. And so if those guys are indifferent, then he will want to drop out right away. He will not find it optimal to wait for those other guys to drop out. And that's the rough intuition, and the details of the proof are in the paper. It's mostly technicalities. So conclusions. Yeah.
So one reason that you may want to wait is if you care what others pay as well, in the sense that if you stay a little longer, the one just above you would pay a bit more. Let's say that's your competition.
I see. So you're saying that if you get extra utility,
what the others are paying.
Sure, absolutely, yeah. So I mean, we ignore all sorts of externalities. You're absolutely right. So conclusions. So the main conclusions are, GSP looks similar to VCG, but it is not the same as VCG. It's not dominant strategy solvable, and truth-telling is generally not in equilibrium. And the corresponding generalized English auction does have a unique equilibrium with explicit analytic formulas for bid functions, which is very useful for empirical analysis. So if you have the data, you can use those bid functions to back out the values or to do all sorts of things. It is a robust equilibrium in the sense that it does not depend on the distributions of types and on beliefs on anything like that. And so no other mechanism encountered in practice is robust yet not dominant strategy solvable. Right? So we have VCG used in practice, but that's just in dominant strategies. So it's natural that it's robust. This mechanism is robust even though it is not solvable in dominant strategies. OK, so do I have some more time? Yeah. Yes, no?
Sure. We always run over.
Well, this is actually not yours. This is Chris's.
We do have time, so yeah.
Yeah, OK. Because I could either stop there or I can talk about open questions. You can go ahead.
Why do we have some time?
Well, we certainly have the time. The question is whether you want to take questions first before you do the open questions or not, but you can decide how you want to go.
Okay, well, let me do the open questions first, and then we'll... So obviously there are tons of open questions, right? There are budget constraints, there are reserve prices, there are externalities of the sort that you just described, tons of possible open questions, but there are a few that, we find particularly interesting. So the most natural question is, should search engines use VCG or GSP? So on the one hand, from our main result, it seems like it makes no difference. The revenues are the same, but we abstracted away from a bunch of different things. So the advantages of VCG are that it reduces the incentives to strategize. It is more user-friendly and allows bidders to spend money on bids instead of bidding software and agents. Right now, if you want to advertise, you have to go and invest in the software, buy Atlas 1.0, and do all those things. If search engines were using VCG, all the money could go instead to just the bids. So the bids would be higher. On the other hand, if some of the bidders are not sophisticated, and instead of going through this whole GSP process and thinking through their bids, if they just go and bid their true values, because that's what Google tells them to do, then revenues will be higher under GSP than under VCG. Yes?
Coming back to the first question that I asked, but it kind of seems that you can even say, okay, then if you do first price, a lot of the things you're saying are truer for first price than for GSP. Like if you bid naively under first price, if you didn't realize it wasn't, then you'd have even higher revenues. Maybe I'm misunderstanding.
No, I think you're right, except that in the generalized first price auction, you will not bid naively, because you're naive. No, and the reason is very simple, right? If you bid a true value under the first price auction, your net revenue, your payoff is 0. You will never want to bid your true value. You're forced to strategize.
I see. Okay.
Right? You don't want
whereas with GSP, you're saying if you're too naive.
Exactly. Whereas with GSP, you bid $10 and they charge you only $8 per click, and you're saying, fine, they're charging me something. It's, and you sort of, yeah. Whereas
with most of the big companies, one would think, are going to not be that naive.
Exactly.
Or even the little guys might go through these intermediate companies, which themselves are not.
Yep. Absolutely. And you're right. Absolutely right. Second question, what happens if strategies are truly dynamic? So, right now, as I said, bidding software doesn't allow them to be truly dynamic. It doesn't allow them to collude. It doesn't allow them to condition their behavior on a specific opponent's behavior, etc. But, even simple strategies, maybe they won't converge. In your simulations, they did, but perhaps some other ways of doing it, and they won't converge. So one interesting question that, I think would be fun to do is to take those bidding agents that they're actually using, Atlas 1.0 or any of those other bidding products, and just run them against one another. And once you guys set it up, you can do it, right? Because it's sort of, you just take those programs, and on a separate server, just run them and see whether things converge, see what the effect on revenues is. A few more questions. One question is, how important is it to multiply bids by the click-through rates? So right now, Yahoo doesn't do it. Yahoo just orders them by bids, and Google does do it. Google multiplies bids by CTRs. Now, on the one hand, it seems like Google's way of doing things is better, right? That's sort of the first approximation. Google allocates things more efficiently in the sense that the higher the expected revenue, the higher you go on the screen. Now, the problem is this calculation, this conclusion ignores the externalities imposed on end users, right? And here is a thought experiment. Suppose you're a bidder on Google, and you can rewrite your advertisement in a somewhat misleading way, in such a way that your click-through rate doubles, but your conversion rate drops by only 49%. So a lot more people click on your ad, but only a few of them, and only a few of those new people will buy something, right? So it's a highly misleading ad, but the net effect is that, so you will be willing to pay, your bid will drop in half, your click-through rate will double, so you will remain in the same position on Google, and you will get slightly more people, right, buying your stuff. So you will want to do it. And it looks like for Google, it's also the revenues won't change. Now the problem is that you now generate tons of people will click on this ad and waste their time, right? So you will impose a huge cost on a large number of people who click on your ad and get no benefit. And if there are lots of people, and if there are lots of people like that, they will start hating your search engine because they go there, they click on those ads, and they don't get any value. Yes?
But you're ignoring the externality of users of reading your relevant ads, right? So if we assume that to a first approximation the ads are roughly correct, then you want to make sure that you're only displaying ads that have a reasonable click-through rate.
You're absolutely right. It's it's basically you're trading.
His example is click-through rate is.
I'm just saying that there's points in both directions.
It's exactly right. So you're right. So you're trading off the externality of people reading irrelevant ads versus people actually following through ads that look relevant but then turn out to be irrelevant. My intuition is that the second type of externality is much worse. If I read something irrelevant, I just ignore it. If I actually click there, I just wasted 15 seconds. So
now the search engines do impose some things so that the ads are not misleading, right? I mean, they try to impose things saying you can't use certain language, you can't, so they attempt to avoid this in certain ways, but I agree with you. There is some incentive to try to play with your click-through rate within those
rules. Exactly. All I'm saying is, the incentives point in that direction, which,
Right. And then there are rules that probably understand this and try to minimize it.
Sure. So the last open question I want to point out is that's actually how we got started in this whole project. How and how fast do bidders learn and converge to an equilibrium? So at any given moment, what fraction of bidders is learning or experimenting? What fraction of them is actually in equilibrium? What fraction is still in the process of figuring it out? And how does that affect revenues and other bidders' payoffs? It's quite interesting. So all of those open questions that they put up and many other questions, I think they all can be answered reasonably accurately, but theoretical analysis can only take us so far. So I think it's very important to do empirical work, experimental studies, and simulations to actually get to those answers. Thank you. Yes?
The Max hasn't said anything.
Okay. So one of the main arguments against the first price is that it puts too much of a burden on the bidding agents, right? And there's this argument, well, if we had pure Vickrey, there'd be less of a burden than if we had generalized second price. But in reality, even if Google switched to pure Vickrey, you're still going to have these robots, right? There's budget constraints. You want to see what time of the day is, you get the most bang for the buck, right? So there's always going to be these robots. And the question is, in practice, do you think that there's more or less of a burden on one of these designs from that point of view?
So here's the difference. You will be using robots in both cases. But in the first case, basically what your robot will be is you have some...
Which one is the first?
Okay, so sorry. In the VCG case, if you're playing VCG, you have this robot. All this robot is doing, you have some Excel spreadsheet with your values by time of the day. So all this robot is doing is uploading your values to Yahoo or to Google, right? Because you don't need to game the system. You just need to report your values truthfully, ignoring budget constraints.
Well, no, but that's the kicker, right? It's in reality you have budget constraints.
So how important? You're right. The question is how important are those budget constraints, and for which fraction of the bidders are they important? We talked with Chris a little bit about that. If it's someone like car insurance company or a travel agent, they do not have a true budget constraint. The only reason they put those in place is to make sure they don't get hit by click fraud. And so that won't change anything in our analysis. Right? If you have true budget constraints, things become more complicated. It's not clear what percentage of the agents has true budget constraints. Whereas if you have GSP, then your robots need to be really sophisticated. You want to monitor what everyone else is doing. You want to best respond to what they're doing. Basically, your robots need to be very sophisticated. It's not just a decision problem. It becomes a game with complicated consequences. So it's going to be a much more complicated robot. So here's a very simple way to put it. Everything that's a problem in VCG will remain a problem in the robots for GSP. But GSP has a bunch of other problems.
Right, but from Google's perspective, it has to weigh the difference in that complication versus the added revenue that they're getting from.
Yep, that's why I said it was an open question, right? do we want to use VCG and make life simpler, or do we want to use GSP and sort of milk the naive bidders? I don't know. Yes.
But in their tutorial, they are telling naive bidders that please don't bid truthfully. Decrease your bid if you are not making enough money from us.
So you think that Google will say that on the website?
They tell us currently, like if you go their tutorial a year ago, they were telling that please bid truthfully because we are using VCG or something. A year and a half ago, I checked in March last year. If you don't go today, they are saying don't bid truthfully. If you are not making enough profit and you want to make more profit, maybe the best position is third position or fifth position. So decrease your bid and do experiment until you are happy with us.
I guess they got smart. Yeah. And I no longer say that they implemented VCG and that you should bid truthfully.
Yeah,
do you have this document where they say that you should bid truthfully?
I don't know whether Internet Explorer keeps that long in cache.
If you can find it, I mean, I would love to have that. If they actually say that you should use
the Wayback Machine. Yeah, you can use the Wayback Machine.
Yeah, please send me the URL.
I followed links from your draft paper, and I found in a footnote of a link, something from what, following links from you, I found something where they still claim they're using Vickrey.
They actually claim they use Vickrey, or they sort of
think I should double check.
I had the link which said that it's based on Nobel Prize winning technology.
Maybe.
I couldn't find anywhere a direct statement that would be untruthful. There were lots of hints that were wrong, but there was no direct statement where you could.
I mean, as long as you have at least one search that results in one search ad, they're technically correct, right?
No, that's fine. Yes.
So in some of the discussion in the front here, there was a sort of presupposition that the big guys are rational or intelligent or something like that. And I actually don't believe that. Now, I don't know that this applies to your theory or whatever, but I think having been in some of these places where we bought television or direct mail for a big company, I never really believed that the decisions were made sensibly or rationally, that they're made for crazy reasons. But to give a sort of, Gedanken thing, if you were to think in your own mind as to whether the government or big corporations gets a good deal on airlines, my guess is that the airlines kind of know that they can soak it to those big, stupid guys and let the rest of us consumers, fly cheap.
I don't know. The stuff I get through when the government pays
You're saying NSF
is
deals
really
are pretty good.
low. It's unbelievable. It's unbelievably low, honestly.
Right, but what about,
I think the right answer is the corporate user. I mean, people who don't travel and don't go over weekends and things like that, they've already set up the fare structure to get companies to pay more, but that's not anything, that's just a rational thing to do. I mean,
a better point, though, the point that comes to my mind is, look, Google seemed to think that they had a Vickrey-like option, right? That there was one large, fairly sophisticated company who thought it was Vickrey-like.
Oh, they couldn't. Do you really think they did? Or I really was under the impression they were just trying to mislead people.
Well,
I mean, they couldn't have been that dumb.
Do no evil, right?
I haven't seen it. I was actually looking around to see whether other people knew they weren't Vickrey-like.
Oh, everybody knows that they were.
Well, no, everybody in a certain community. I think the question is how broadly.
So here's my take.
I think there's at least some reasonably smart people, right? Advertisers are not computer science or auction theory theoreticians who, right.
But it's kind of one of the first things you would have in an auctions course, do this.
Do you think most marketing people have taken an auctions course?
Here's my take.
Let the speaker speak, right?
Here's my take on this. It's actually, so there are some message boards where you can follow the discussions of those guys, and I actually met some of those guys, and there is a distribution. Some of them are dumb, but there are some remarkably smart people. It's basically, do you remember this guy Brendan Kids, right? So he actually runs those things, right? He organizes those campaigns, and he understands all the minor details of the bidding software. He understands everything about the mechanisms. He understands everything about how they can be gamed, about retaliation. Lots of those guys are very sophisticated. Lots of those guys, there is this forum called Webmaster World where they have sort of sections for, Google AdWords and Yahoo. And basically, they understand everything really well. They ask very detailed questions about minor details of mechanisms. They know it's not true. They know everything. Yes, they're not all of them. Not all of them. Definitely, there is some distribution, but many of them understand everything very well. So I mean, basically, I think if there is any setting that we can have a hope of, having rational agents playing against each other, this is as close to it as it gets. They're just, that.
Whereas you're saying the airline price tickets is probably not as good a deal.
Well, I mean, I don't know. They're actually pretty rational on the other side. Or the airlines try to sit there and figure out how to make the most money. And the buyers of those tickets may not be rational, but the sellers are.
I don't know. The sellers aren't making a whole lot of money.
We started there.
Yep.
Right?
Yeah, we started there. Exactly.
You made one assumption, I believe, which was that eventually all the bidders would be able to figure out everybody else's true value.
So that was in the first, yes.
And my question is, how critical is that assumption?
Well, so in the second model where we have the generalized English auction, we didn't use that assumption. So that's why we have two approaches. So that's why we couldn't sort of tackle it head on. So we took two approaches, and in the second one we just assumed it's private values. We did not assume that they know each other's value.
But in effect, you're assuming that you know the values of people that are behind.
That's right.
Know you.
Yes.
But you don't know the value.
That's true.
I was a bit confused. Why do you assume this? It's a little bit weird, the knowledge structure that you assume that you know the distribution for the guys above you, but only about exact values of.
It's basically, the interpretation that I gave is, you come into the market, you start bidding low, and then you just keep increasing your bid as long as it makes sense to do that.
I mean, does the
which is a pretty
software have
natural
access to these numbers? So assume you would run this auction. Would the software actually, the gaming software, would it have access to these numbers? Or would the gaming software just see the result of the auction and doesn't see? You see, because in practice, probably what happens is you input your bid and the machine decides how to order them. And you actually don't see what the machine is doing, so you don't see whether it would do a combinatorial auction or whether actually instead of running it combinatorially, it runs it from the bottom up.
No, that's why one of the open questions that I had was, it would be tremendously interesting to just take those bidding agents, feed them some numbers, and see what happens.
Also, you want to tell them, look, the people under you are this, but above you, I don't tell you.
Well, that was the assumption in the first lemmas in the GSP work.
So, given your knowledge of these bidding blocks, I don't know if you know how familiar is the ascending auction, is that a good model? I mean, if I assume there's a new keyword, there's one bidder, they're going to bid as low as possible, and then they kind of sequentially come in, do you think that's kind of what would happen?
So I think, looking at the first slide, with the first price auction, it seemed that that's what they were doing. So you start low, and then you try to outbid others as long as it makes sense to do that. So I don't think it's an unreasonable. I mean, it's possible that that's close to what they're doing, but who knows? Who knows?
The assumption there is that no matter what, you are going to be included in the auction. There's no way that you can start low, say, I'm not interested in competing unless I get a slot up towards the top. But then once the price raises above a certain amount, just drop out of the auction altogether. I can't drop out and be not included. I drop out and I end up in the slot.
That's right. I see. Yes.
So you're forcing competition on the system, is what Jody's saying.
The reassuring thing is that it's an ex post equilibrium. So at least in the world that we're setting up with our assumptions, you will not want to drop out. So even after you see how everything played out, you will not want to say, "Oh, now I want to drop out." You will never want to say that. You will be happy where you are.
Because the one wrinkle is that the values change over time, and so what's stable now might not be stable.
Absolutely.
In practice.
Absolutely.
And the cost of actually maintaining, watching for if fraud is occurring, having the data stored, etc., is going to be some cost. So unless you get up to a certain number of expected clicks, you may have enough cost that you just never achieve.
Sure. So there are fixed. Yeah, absolutely.
Somebody mentioned the airlines bidding for seats. Now, the other day or the other year, Wall Street Journal wrote up that the airlines that are incredibly clever about pricing seats are the ones that are so near bankruptcy it makes no difference. And the two airlines that make any money have that stupid simple pricing schemes. Now, there may be a cause or maybe effect, but